Continuing on physical chemistry, chapter 15, we're in section 7 now. We're going to talk about molecular collisions and mean free path. Now we derived this function g of speed that is the result of collisions. Now we derived it showing collisions between the molecule and the wall. But in reality there is no wall. It's actually the collisions between gas molecules. Now reactions also occur as a result of collisions, which is why we're learning this even as in a chemistry class, because these collisions enable chemistry. Now, one assumption we've been making, though, is that the molecules are actually hard spheres. Now, in reality, they come in different shapes, of course, and they can actually behave more like sponges than a hard sphere. Now, another assumption we're going to make, of course, is that the molecules are spherical. Again, they come in different shapes, but this is just to simplify the math. And then another assumption that there are no intermolecular forces among the molecules except at the actual time of collision, which again isn't technically true, but it's going to make the math a lot easier, and it'll be close enough for now. So let's say we have two different molecules, B and C. Oops, forgot to write the C here. Hang on. B and C. So we've got B and C here. So the distance, so B has a radius of B, so a diameter of B, right? And then molecule C has a radius of C, so a diameter of C. So the distance between them, center to the center, will actually be the radius of B plus the radius of C. So again, R sub B will be the radius of molecule type B, and then RC will be the radius of molecule type C. Now, another assumption we're going to make is that collisions are elastic, which means, all the kinetic energy, momentum, and so on is conserved. So we have a lowercase z here, and then I'm going to write uppercase z like that, just so you can tell them apart. So we have this lowercase z from B to C. That means the collision rate for one particular B with any other C molecule. And then we're going to have this capital Z, BB, which means the total collision rate for any B molecule colliding with any other B molecule per unit volume. And so ZBC would mean the total collision rate for any B molecule colliding with C molecules per unit volume. So we're going to have N sub B will be the total number of B molecules, and N sub C is going to be the total number of C molecules. So what we want to do is find what is ZBC. So here's B and C next to each other. So we have this imaginary cylinder. Its diameter, we're just going to call D, of course. It's going to be the diameter of B plus the diameter of C. And of course, the diameter is twice the radius. So we have D is equal to 2 times the radius of B plus the radius of C. Now we're going to have capital V for the volume of this imaginary cylinder. And then we're going to have average B sub V sub BC. That's going to be average speed of B molecules relative to the C molecules. Now a collision occurs when the distance between the B and C molecules, it gets within this range of RB plus RC, which of course is 1/2 of the diameter of B plus the diameter of C. So the average speed of BC dt, that's the length of the cylinder. So speed times time is distance. Lowercase t, of course, is time. Now, the area of the circle at the end of the cylinder is just pi r squared. But remember, it's the radius of both. So we have pi times the radius of B plus the radius of C squared. And of course, volume for a cylinder is going to be area times the length of the cylinder. So we have volume is equal to pi times RB plus RC squared times the average speed of the BC times the differential of T. Now the number of C molecules with their center in the cylinder is going to be this speed cylinder divided by the total volume times NC. Now this V is the speed of the whole, or the volume of the whole container, not the, oh yeah, so it's the volume of the cylinder divided by the total volume of the container times the number of molecules of C. Now this is assuming, of course, that they're evenly spaced out, which at any one time might not be correct, but if we're looking a long enough time, it'll average out and it's good enough. So the number of collisions which a specific B molecule makes with any C molecules, remember, is lowercase z bc. So that's going to be equal to the volume of the cylinder divided by the total volume of the container times the number of molecules, C molecules, divided by time. So we have equation 1, which is ZBC is equal to NC over V times pi times RB plus RC squared times the average speed of B with respect to C. Now we need to substitute in for the average speed, VC. Now remember, collisions can occur at any angle, but for simplicity we're just going to assume it's a 90-degree angle right now. Now actually, that's not really an assumption, it's actually the average angle. The collision can be between 0 and 180 degrees, so 90 degrees actually works out to the average. So when a B molecule collides with C molecules, you can have several things that can happen. So if they're moving in the same direction, 0 degrees, or they're moving in opposite directions, that's 180 degrees, or they can be perpendicular, that's 90 degrees, or they can be any other angle. Now, like I said, we could pick any angle to be average to collision angle, but we're going to just arbitrarily pick 90 degrees. Now here's the Pythagorean Theorem again. We have the average speed of the B molecule versus the average speed of the C molecule. So we're going to get this speed of B with respect to C. So 90 degrees, they're perpendicular, we can use the Pythagorean Theorem. So the average speed of B with respect to C squared is going to be equal to the average speed of B squared plus the average speed of C squared. So we also have the average speed is going to be equal to the square root of 8RT over pi m. We showed that before, it's the previous section. So we have the average speed of B squared is going to be equal to 8RT over pi mb. And that would be the molecular weight of molecule type B. And likewise, the average speed of C squared is going to be equal to 8RT over pi times the molecular weight of C. So now we're going to substitute both of those back into equation 1. So we have lowercase z, so the speed of B with respect to C is going to be equal to the number of molecules of C divided by the volume of the container times pi times the radius of molecule B plus the radius of molecule C squared times this whole quantity of 8 times RT divided by pi times 1 over B plus 1 over MC to the 1/2. That's just the Pythagorean theorem. And again, V is the container volume, not the cylinder volume. Now, if C is equal to B, then that's the special case where we're talking about a pure gas. So then we can just put in ZBB is equal to NB over volume of the container times pi times 2RB squared times this whole quantity 8RT over pi times 2 over MB to the 1/2 power. So now we're going to prove that NB over V is equal to pressure B times Avogadro's number divided by RT. Now we're going to assume for now ideal gas, so pressure volume is equal to nRT, and then of course PV is equal to number of molecules divided by Avogadro's number times R times T. We're going to solve that for volume, so we get volume is equals the number of molecules times RT divided by pressure times Avogadro's number. So we have 1 over volume is equal to pressure times Avogadro's number times the number of molecules times RT. So we get NB over V is equal to P NA over nRT times the number of molecules of type B. That's going to be equal to the pressure times number of molecules of type B times Avogadro's number divided by the total number of molecules times RT. And that's just going to be equal to the pressure of molecule B times Avogadro's number divided by RT. So ZBC is a specific B molecule with C molecules. ZBB is a specific B molecule colliding with other B molecules. So for pure gas, remember, RB plus RC squared becomes RB plus RB squared equals just the diameter of B squared. So dB would be the diameter, not differential, of B, molecule B. So we get ZBB is equal to pi times the diameter of molecule B squared times the square root of 2 times the square root of this whole quantity, 8RT over pi times the molecular weight of B times the partial pressure of B times Avogadro's number divided by RT. But remember, ZBC, this is capital Z now, that's going to be all B molecules and all C molecules. ZBC is going to be the number of molecules of B times this lowercase ZBC divided by the volume. So that's going to be collisions per unit volume per second. And that's going to be the total collisions per unit volume. Or this, well, it doesn't say per second, but you get the idea. So ZBC is going to be equal to pi times the radius of B plus the radius of C squared times this whole quantity, 8RT over pi, times 1 over MB plus 1 over MC to the square root, all this square root, times the number of molecules of B divided by volume times the number of molecules of C divided by volume. So ZBC, or ZBB, is any B, so we can, with any B, so we can introduce 1/2 factor to avoid double counting. Because we don't want to count A colliding with B and then also B colliding with A. We just want to count that pair once. So ZBB is going to be 1 over the square root of 2 times pi times the diameter of B molecule squared times the square root of 8 times R times T divided by pi times the molecular weight of molecule B, and then all that times the quantity squared, the pressure of molecule B times Avogadro's number divided by RT. Now let's, as an example, let's talk about oxygen molecules colliding. Now the diameter is roughly 1.2 angstroms. So, oops, is that supposed to be radius? Because this says diameter is 2.4. Whoops. There must be a typo here. I'm going to have to look into that. So, is this radius? Whoops. Okay. So, the bond length. So the bond length of an O2 molecule is about 1.2 angstroms. And of course, 1 angstrom is 1 times 10 to the negative 8 centimeters. So the diameter of an O2 molecule, we're going to say, is roughly equal to 2 times 1.2 angstroms, and therefore 2.4 angstroms. So that's our diameter of one oxygen molecule. So ZBB, that's going to be roughly equal to 3.4 times 10 to the 28 per centimeter per second. And that's for oxygen at room temperature, because we said 25 degrees Celsius, 1 atmosphere. So the average speed is going to be the square root of 8RT over pi times the molecular weight. So that comes out to 444 meters per second at room temperature. Now let's talk about mean free path. Lambda is going to be the average distance a molecule travels between 2 successive collisions. It's another way of saying that is the average distance a molecule travels between collisions. Now again, let's talk about, for a given B molecule, the distance traveled is going to be the average speed of that B molecule times time. and t is any long time. So the number of collisions that B makes is going to be equal to this function of z of b plus z of b of c times time. So it's B colliding with other B molecules, and it's B colliding with the C molecules. So lambda of B, that's the distance there between collisions, is going to be the average speed of the B molecule times time divided by this function times time. Notice time cancels out, so that's why I wasn't too worried about how long of a time. It doesn't matter, it's going to cancel out anyway. So we have the average speed of the B molecule divided by this function of B against B plus the function of B against C. So for a pure gas B, ZBC is equal to 0 because there are no C to collide with. So lambda will be just the average B divided by Z of B of B. Now we got Z of B of B, so we can substitute in. It's the average B divided by the square root of 2 times pi times the diameter of B times the average speed of B times n of B over V. Now we found out this velocity for oxygen earlier, but it doesn't matter. You'll notice the average speed of B is going to cancel out. So we end up with the number of molecules of B divided by volume is equal to Avogadro's number times pressure divided by RT. So we get lambda is going to be equal to 1 over the square root of 2 times pi times the diameter squared, all that times R times T times P over Avogadro's number again. So since pressure is on the bottom, what that should tell you is that as pressure increases, lambda is going to decrease, which should be obvious because if pressure is more, that means the molecules are closer together. They're going to collide more often. And of course the units for lambda are length because we're talking about a distance that is going to travel before colliding, on average. So of course the gas constant R is just 82.06 centimeters cubed atmosphere divided by mole Kelvin. So if we have diatomic oxygen gas at 25 degrees Celsius in 1 atmosphere, then lambda turns out to be just 1.6 times 10 to the negative 5 centimeters, or about 1,600 angstroms, 1,600 angstroms. Now if pressure is 10 to the negative 9 atmospheres, which is a pretty low vacuum, then each molecule will collide about 2.8 times per second. So applications of this are, transport properties of gases. All right, that is the end of section 7 in chapter 15.